I'd like to thank Sustain team for inviting me to basically discuss my concerns over the general thought process for the industry of moving forward with hydrogen. If you could next, please. And I apologize for our, I'm having technical problems as well, both from sharing point of view and hopefully not audio at the moment, but audio has been a problem this morning too. I'm going to basically look at the hydrogen economy and the thought process of hydrogen DRI and the EAF, looking at the future forecast and issues I believe are evident in the potential of using the DRI. Look at alternatives that we might explore further in terms of the blast furnace BOF and also the DRI and the EAF before I summarize. Next, please. We all know that it's the preferred CO2 mitigation process for the future, hopefully attaining something like 0.02 tons of CO2 per ton of steel. In 2019, we had almost 28% of the world's steel from EAFs, and we're predicting moving forward to it probably closer to 74. And of that, 50% will be from scrap and 50% from ore. And of the iron produced in 2070, 0.575 tons of DRI is going to be from, of the iron is going to be from DRI, whether it's hydrogen or natural gas based. Next, please. Next, sorry. I've done a quick calculation. One of the biggest issues I believe is going to be construction rates. The DRI plants have gone from 0 to 104 million tons a year in 50 years, which is approximately 2 million ton plant a year. And if you look at 2050 and 2070, you're looking at 14 or 13 DRI plants a year. The terawatts for that are about 8.4 and 173 when you move to 2070. And that constitutes 3,898 20 megawatt PEMs, which are pretty standard at the moment, and 8656 when you get to 2070. In terms of the EAFs, you're looking at 551 new 2 million ton a year EAFs, or 700 when you get to 2070. And then if we look at the green energy, this was a quick calculation and it's a bit on the low side in terms of kilowatt hours per ton of liquid steel. But basically, if you're going to use 80% zero carbon DRI in the arc furnace, you're going to look for an additional 290 terawatts. Next, please. The next issue is cost of steel. Not only do we have the cost of new mills and infrastructure, but the zero carbon DRI is going to make steel cost $1,327 a ton of liquid steel if you use the IEA numbers. And this is at 2030, not even 2050. CRU, on the other hand, say that it's going to be $3,700 per ton of crude steel. And they're looking at $200 to $300 per ton of carbon tax, which would incentivize 60 to 90% of the steel makers in Europe, respectively. ArcelorMittal has stated that their cost of production is going to go up 50 to 80% if they use hydrogen DRI. And the other issue is going to be the worldwide competitiveness against people that are not going to comply. And we've already got a problem, as you can see from this chart, of USA being more expensive even than the Europeans, never mind the Chinese. Destruction of the current BOF blast furnace infrastructure and downsizing of manpower is going to cause social implications. And of course, there's some major challenges for zero carbon DRI in the arc furnace. Next, please. What are they? Basically, they're going to reduce chemical energy, which is now 30 to 50%. We need to find some possible replacements. You're going to have slower bath reactions. You're going to have lack of phony slag, which has its own issues, reduced productivity, yield, heat transfer in the bath. And you're going to need more carbon in, whether it's injected or we have an efficient OBM situation or base metallics, or we can use tire wastes or other materials, but it's going to require more oxygen, which is more CO2 and more power. More power is going to cost us between 0.3 and 1 kilograms of CO2 per kilowatt, depending on the source, hopefully green, but in the US, it's going to be an issue getting green power. Increased gangue will come from not only the DRI, but also the FEO going to the slag, and that's going to create more slag because of lime needs. And the other issues which would create more kilowatts and lower yield are going to be, you need a higher temperature to melt if you have less carbon. You're going to have to rethink the refractories because there's going to be carbon dissolution and erosion from the slag FEO. You're going to need a deeper bath because without the foamy slag, you're going to need a greater volume, and that's going to require bath stirring, and most of the steel makers have been fighting using that for a long time. And again, we have degradation of the ore, which will compound the gangue issue. Next, please. Scrap in the EAF, there are some issues there. Obviously, one of the biggest problems is cleanliness in terms of organics and residuals. We've seen some reports saying that cleaning will increase yield up to 98.5%. Multi-passing through a shredder will eliminate copper. And the question becomes, are there thermochemical options out there to reduce residuals further? There's going to be a dearth of quality scrap in the future, and we need to look at how we can utilize that. And we've also got a big issue with the volume of scrap that will be coming out of China soon. So currently OEMs are required to a large extent for high quality steel. Next, please. So some of the alternatives, 97% of the ore that's taken out of the ground right now is for blast furnace quality only and not viable for DRI and into the EAF. Kobe Steel currently has managed to lower the coke rate to 239 kilograms per ton of hot metal this year in April. And experimentation has been such that 21% hydrogen has been achieved, but question is that really the max as is being specified? In the US, Cleveland Cliffs, they've used natural gas, basically saying, hey, that's got 4 hydrogens, and they are predicting that they can reduce their CO2 by 25% by 2030, stating that their scope 1, 2, 3 are basically lower than those of the electric furnace flat roll products in the US, being 1.63 versus 1.8 tons of CO2 per ton of steel. But that's mainly because they're expecting 50% use of imported pig iron, and they've associated 1.1 tons of CO2 to that particular import. They're looking at pellets in the blast furnace, which reduce the CO2 85% versus sinter. Natural gas blast furnace Twir injection at 115 kilograms of natural gas per ton of hot metal has reduced CO2 9% versus coke alone, and that's saving them 1 coke battery a year. The HBI in the blast furnace has increased productivity 8%. Coke rate has reduced 7% for every 10% of HBI input. And they're saying 70% reduction in CO2, of course, comparing to imports of pig iron and DRI HBI. Hatch, on the other hand, have looked at hydrogen Twir injection with PCI using 35 kilograms of 900 degrees centigrade hydrogen, 20% reduction in CO2, 1.8 gigajoules, which is 35% increase in the energy to the steelworks, and 100 kilograms of coke reduction, but that's going to cost up to $110 per ton. Now, if you add top gas recycle and CCUs to that, he's anticipating 80% reduction in CO2 if you use the blue and green hydrogen, and that equilibrates. Hatch is saying to hydrogen DRI in the EAF at 0.4 tons of CO2, but technically that can be as low as O2. Next, please. I'm sure the team at Swinburne that talked this morning looked at the scrap coolant to increase productivity and reduce CO2. Currently in the world, it's 17%, and the US, it's between 20 and 25%, and 40 to 45% has been tested. And Swinburne believe strongly that it can be up to 40% quite easily. The other issue is adding HBI in the BOF, which has a higher cooling intensity. It's about 20% better than that of scrap. Next, please. So an alternative is scrap in the EAF. If we can clean up the scrap, currently we can get 0.18 to 0.4 tons of CO2 per ton of steel, depending on whether it's renewable energy or not. But we need to beneficiate the scrap. We need to have a mentality change to pay for preparation and the quality, both at the scrap dealers and in the steel industry. And we need to still have carbon. In situ carbon is much more efficient in terms of reactions and performance. So we need to find some mechanism to import some good efficient carbon to the furnaces, and possibly continue to use the DRI, the hot metal pig iron and granulated pig iron, and save the infrastructure of the OEMs. And of course, DRI is an option, but preferably with carbon, because it has no sulfur, no ash, no volatiles, and no residuals. Next, please. If we are going to use scrap in the EAF, we need to, apart from improve the quality of the scrap, as I've said, we need to look at programs or models that will allow assessment of value in use charge optimizations, incorporating that, and to use off-gas analysis to maximize the chemical energy inputs, minimize off-gas system heat losses, which can be as high as 36% of the input energy, and increase the safety, of course, by reducing explosions. And there's an example on the right, which I'd love to go through, but I don't think there's enough time. But if you optimize your scrap, you can, in this particular instance, save $15 per ton. Next, please. Of course, the other alternative is to definitely look to the future using alternate irons with the scrap, because it will add chemical energy and you will have cleaner steel. Nitrogen is not going to be a problem. It can be reduced down to 10 ppm for melt and 28 ppm for billet. You also have, if you're charging hot, a lot of benefits financially and energy-wise. As you can see, 20 to 30 kilowatts per 100 degrees C. Same for hot metal and pig iron. And you have a better refractory life yield and FEO recovery. And of course, it can be continuously fed, as can the granulated pig iron that's now being looked at seriously. Next, please. So in summary, hydrogen DRI EAF steelmaking is going to be costly, and it has some major techno-economic challenges, which I don't believe are truly being addressed at the moment. It's going to compromise competitiveness. It's going to be very dependent on the ability to supply cost-effective green energy and hydrogen at the capacities that are required. And we need to find alternative chemical energy and foamy slag sources. The alternatives, of course, are to upgrade scrap, maximize the use of scrap in the not only the electric arc furnaces, but also in BOFs, I believe. We should look at in-house scrap management, which a lot of the US, I think most of the big US steelmakers now have their own in-house scrap dealers. But we also need to look at developing CO2 mitigating alternatives for the integrated mills so we can minimize their carbon footprint. And again, look at new technologies, but I'm not sure we have the time to do that. There is a project ongoing right now to look at biogenic carbon containing DRI and incorporating that with CCUs, which will give us zero carbon footprint technically. New steelmaking processes, I don't know whether that's viable. We've been looking at new processes for the last 35, 40 years, and we really don't have any that are at full capacity. So with that, I'd like to thank you for your attention. Hope I've not gone too far over time, and look forward to answering questions during the question time.